Thank you everyone for coming. Thank you, Alexandros, for the great invitation. I'm very happy to be here for me. And I'm going to tell you something about BIM and the DfMA technology, the most innovative technologies we can use for timber constructions. So very quickly, short introduction. I started in 2003 engineering timber buildings, and at that time we were really pioneers in this field, but we still feel like we are a bit pioneers in timber engineering, because every day there is something new to learn, every day there is a new project to work on. And I like to show you this map because it shows how we developed our business in the past 15 years. We started from a little village in Italy, and now every pin shows where we engineered at least one project, at least one building. But the main reason I'm showing you this map is to show you how timber can be engineered in one country, in this case in Italy, in the Alps, and then can be produced by someone else, by a factory, wherever in the world, and can be transported everywhere. So I see timber more than a simple material. I see timber more something like a new technology to explore, a new way to design for us as engineers or as architects. Ergodomus is an engineering company, and we are located between the producers on one side and designers, general contractors, developers, and builders on the other side. This means that we work at the same time for many different types of clients. So we know how manufacturers work, we know how designers work, we know how builders work. We know what architects want, and we try to do our best to make them happy, and we try to get the most out of timber every time for every single project. Let me show you also something great. This is the diagram showing you how the production of CLT globally changed in the past 25 years. In 1995, the global production was about 25,000 cubic meters per year. 10 years later, 130,000 more or less. 5 years later, we're talking about 300,000 cubic meter. 500,000 cubic meter 9 years ago. And the timber industry produced more than 1 million in 2018. So as you see, there is a big exponential growing of the production of CLT all over the world. If someone asked me, why should I go for CLT? Why should I study as an engineer or as an architect? Why should I improve my knowledge of CLT? I just send this diagram. This tells us that it is the solution to go for. It is the material to go for, definitely. But CLT, as I said, it is not only a material. I think it brought a big revolution in the market. Because with CLT, we can really see timber as a digital material. It can be very easily implemented in a BIM workflow. It can be used for computational generative design, as I will show you later. We finally are talking about robotic prefabrication and CAD/CAM technologies. It is not more a science fiction, it is something we are using. We've been using for years. DfMA is an acronym. I really love this. It stands for Design for Manufacturing and Assembly, and it means that once we design a new timber building, a new timber structure, we are immediately thinking about how the element can be produced, transported on site, lifted, and assembled together. We cannot design, we cannot engineer a timber building without having in mind how the elements will be produced. And in order to improve this knowledge, in order to be sure that on site there will be no problem, they will assemble all the elements without delay. We implemented some new technologies in the office, and this is the augmented reality. this is how we analyze the details in the office. We want to be sure that the detail, that the elements can be assembled together. We want to be sure that the dowels, the steel plates, etc., are okay. You see here how my colleague can just press on a button and you can see how the detail must be assembled by the assemblers on site. To do this, you need to have a very holistic view of the project. And to have this holistic view, in my opinion, you need to raise your point of view. If we stand at 1 meter, you just see your feet and you do not know anything else of the building. So you need to go up 5, 10, 15 meters and above, because you need to have a global view of the project. You need to know exactly how the project would look like. You know, to see where the CLT panels can be stored, how the trucks can arrive to the site, how the lifting crane will work. And this is the way, this is my way, my view of the timber sites. Please raise your point of view and have a global view, have a holistic view of the project. It's the only way to be sure that you will not have any problem on site. I'm sure there are some architects, there are some engineers here, and this is the most frustrating part of our job. You dream something, you talk to the client, then you prepare some drawings, but then you get this on site. Why does it happen? Because we like to change everything once we prepare the drawings. We arrive on site and we decide to change the size of the openings, we decide to move the windows, etc. With timber, I prefer to say what you draw is what you get. You draw something on your computer using the software you like, and then you get that element on site, exactly as it was on your computer. I know many of you, I'm sure many of you are familiar with 3D printers. The workflow is exactly the same. The only thing changing is the size of the elements. Here we're talking about 50 by 50 by 50, more or less, the maximum size. When we talk about CLT, as we saw in the previous presentation by Albino, we're talking about bigger element, up to 12, 13, 15 meters long, up to 3.5 meters wide. The workflow is that you draw something on your computer, you dream something, you create a detail, no matter the complexity, there will be a CLT machine creating the element you draw, creating the solid element you draw. And before arriving on site, we give our clients the possibility to check everything thanks to the IFC files. So this means that weeks before having the CLT panels on site, you open an IFC file, you just click on an element, and you see who the element is. The thickness of the element, the number of layers, the timber grade, and the assembly number. You can check these 5, 8, 12 weeks before having the CLT panels. So when you get the material on site, it is not a surprise. It is not something like you go on site and you say, hopefully I will get what I wanted. You will get what you will see, what you saw weeks before on the IFC file. This can be called the digital model. This is the digital model of the building you will receive on site. And you can check the digital model, as I said, weeks before the CLT panels arrives on site. So this means that you can check all the detail, no matter the complexity. This is the two elements of a bracing element. These are the two beams on site And this is the drawing in Revit. This is the drawing we sent to the client. So they can approve it. They can say, I do not like the shape of the building. I do not like the shape of the beam. Please change this, this, and this. And you just move lines, which is quite cheap. Changing something on site costs a lot of money, a lot of time, and makes the client very unhappy and worry. We are all familiar with the Matrix, with the movie Matrix. I like to make this comparison. In timber, we see our building, we see our project as a huge bucket of numbers. So this is the digital model of a building. It is made of timber, it is made of partially of steel, it has dowels, screws, nails, etc. But for us, it's just a digital model, which gives us a lot of advantages, because we can even check how the CNC machines will work in the factory. So this is something, we have no CNC machines, we have no factory, but we can check in the office, we can check how the CNC machine will work, and we can check if they will work properly. Of course, here we increase the speed of the CNC machine. It takes minutes and minutes to machine this element. But once we send the files for the robot we created, we know we can check if it is accepted by the machine, if we talk the same language of the CNC machine. Having a digital model gives also us the opportunity to quickly share the drawings among different software. So this means that we can combine together FEM software, BIM software, Rhino, Grasshopper, and we can use one of those products as a hub. From this hub, we create a file from a single source. We create a file for the FEM software, for Revit, for ArchiCAD, Allplan, for the CNC machines. And everything is a huge amount of numbers. It is just the model. We are just using in the best way the digitalization of the model. Let me show you some examples of some projects we worked on in the past years using these technologies. And at the very end, I will show you a very special project we worked on for weeks, which will happen in Australia in August, September, we hope, because we made a lot of experiments, a lot of tests on this project to see how we can use double curved beams made of timber. This is one of the very first multi-story buildings we ever designed. It is in Modena. It is an area in Italy where we can have quite strong earthquakes. We have the last one in 2013. And this, the fact we had this earthquake made the people less skeptical in having timber, because they saw what can happen on a concrete building in case of earthquake. And they saw that timber can solve the problem. I'm not saying that if you go for timber, you will never have problems during earthquake, but I'm just saying that timber, for sure, as we saw before, is a very good material to go for in a seismic area like this one, or like we have in Italy as well. We're talking about a 6-story building, and as Albino said before, the average is that you can build 1 floor per week. Can you imagine to build 1 floor per week, how fast they are in assembling the elements? But what is even more amazing is that we started from a digital model, and here at this stage, architects, designers had the possibility to tell me, I need an opening here, 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 with this size. I want to move the opening 10 meters, 10 centimeters above, 10 centimeters left or right. And you can do this without any extra cost, just working on the digital model, just sharing IFC file, just sharing the file in Revit, ArchiCAD, Allplan, or whatever the software you use. Then they approve, they sign this drawing, and they say, this is what I want to see. This is what I want to have on site, and they will get it. We made it was quite a challenge here because we wanted to have a very big CLT panel for the shaft, because everything it is made of timber. There is no concrete. We use concrete just for the foundations, as you can see here, and this is the element you see here. So we're talking about a very big CLT panel, which is 2.5 meters times 15.5. Together with the developer and together with the architects, we decided also to use a CLT for the stairs, and you can see how they look like before being installed. The ramp is made of CLT, and then the steps are made of glulam. You do not have to draw the stair on the wall and be worried about will the assembler, will the craftsman work properly on site? Will I get the stair as it was in my drawings? They produce the element off-site, they bring the element to the site, and they just install in a few seconds, in a few minutes, the stair on site. Then you just need to cover it or to leave it partially exposed. It is up to you as a designer. The stair you install at the very beginning of site of the assembly can stay there. You do not have to remove it or to rebuild it. It is a temporary stair, but it stays there for weeks, for months, forever, during the entire life of the building. Having the earthquake, we also had very big lifting forces, horizontal forces, and of course we had to go for quite big steel plates. I'm 1.83 meters tall, and as you can see, the steel plate will be around 1.70 meters in this case. This is a structure we engineered for the Biennale in Venice in 2016. We had just 10 days to assemble everything and to bring to the water. So to do this, again, we used very deeply the potential of we used the potential of the digital model. You see the digital model here in the middle, the production drawings, and here you see the assembler when we were making the first test before putting the structure in the water. Another project, this is a headquarter of a company in Parma, inside the university. We're talking about a 4-story building, and again, 1 week per floor, and they completed the structure. Together with the developer and together with the university, we decided we had a request to reduce as much as possible the thickness of the slab. So we created ribbed panels, and all the installations run through the structure. But all the holes were made off-site in the factory, so that we didn't have to create those holes on site, those recesses on site. We didn't have to make it. Off-site, in my opinion, always wins. Must win. You see here another detail. We have a hole and the installations going through it. This is another technology we tested, and it is a modular building. We engineered it in Norway. It is an 8-story building, where in reality there are 4 8-story buildings. As you can see here, we engineered modules, and the size of the modules is 4.2 meters, 3 meters by almost 12, 11.8, 11.5. And they assembled an 8-story building in just 13 working days. We're talking about 110 modules. They assembled more than 10 modules per day. At the beginning, they were a bit slower, and then they get faster. And this is the technology they used. This is the reason they were so fast. We helped the company to develop a super innovative connection to speed up the assembly of the elements so that they almost do not need screws to connect together the elements. Just a few amount of screws, and they connected the elements, the modules together. This is the FEM analysis of the building, and this is how it looks like today. As you can see here, nobody can say this building is made of timber. You cannot say that. All the timber elements are covered. There is a nice facade, a ventilated facade. You see some elements for the ventilation. You see the windows. You cannot say that it is a timber building, and you cannot even say that it is a modular building. Another very innovative project is this one. Is a headquarter of a company in the northern part of Italy, in the Alps. It is a super hybrid building because it is made of concrete, steel, and CLT. The facade is made of CLT because the architects wanted to have hundreds of openings with a different size and placed in a very specific position. And CLT was the cheapest solution to go for. So we started working together with them, sharing the files in Rhino and Grasshopper, and testing a workflow to transfer the files, the drawings from Grasshopper to the CNC machines. Here you see some pictures, concrete, steel, CLT, combined together. I think if we want to promote the use of timber, we cannot be purist like either 100% timber or nothing. We need to combine together different materials to get the most out of each of them. So if they asked me, are you happy with the timber buildings? Absolutely yes. Let's go for a hybrid. Steel, concrete, timber, getting the most out of each of them. This is the digital model, and this is what they built on site. The IFC model is this one. Once again, the designers, the builders had the possibility to check everything on the 3D model. We shared this file weeks before starting the assembly of the CLT panels, weeks before starting the production of the CLT panels. And here you see thickness 100 millimeters, the length, the width, timber grade, position number. Lotto 1 means it will arrive with truck number 1. So you can even know when the element will arrive on site. If we're talking about a container, here you see the number of the container, the row of the row where you will find the element. So you know if it is at the top or at the bottom of the container. The very last project I'm going to present to you is the one in Australia. I'm very proud of this project because we spent thousands of hours to develop the workflow and to develop the model. But now I can share with you the shape of the building. Well, it is not really a building. It is a super expensive roof. which is made by single curved beams. The yellow ones, red ones mean the red color on the outline means double curved and twisted beams. Green beams here are straight. Here we used software like Rhino and Grasshopper to create the digital model, to create the elements, and then from that model, we even prepared the files for the CNC machines. So we could control everything on the project in this case. Every single detail of the project is a parameter in Grasshopper. I don't know who is familiar with those tools like Rhinoceros and Grasshopper combined together, but this really opened new doors for us. It gives us inspiration for many other ideas we're working on. And what is amazing is that the connection between the double curved beams and the straight beams are made of steel plates with an L shape. The algorithm we created allows us to change the shape of this beam and to update automatically the production drawings of 800 elements made of timber, made of steel. So we worked together with the architect in finding the right shape of the beams, but now, fortunately, they will never change the idea because they have produced everything. They are complete in the production. But during the design process, we could move this beam, and automatically the length of this one, this beam, and this one will change, and automatically the drawings, the production drawings of the steel plate were updated. And as I said, we have more than 800 steel plates parameterized in Grasshopper. So there is a huge algorithm. And my colleague, again, is like in the Matrix movie. He sees an algorithm, but then when he runs the algorithm, he sees the geometry. So the geometry is created by an algorithm. It is not like you draw in the old way, line by line, circle by circle, element by hand. You create the algorithm, and then you get a 3D model, so that you can quite quickly change every parameter. Those are the connections between the double curved element beams, red, and the the straight beam here in green. Another example of the connections between the two elements, we decided to go for slotted steel plates which are completely hidden inside timber. So from outside you will not see any steel element, any steel plate or any steel dowel. And this is just a small part of the algorithm. It is a huge piece of paper. We printed in the office just to know what we did. Every line connects a different component in Grasshopper, but allows us, with some slider, to change the shape of the building, to change the curvature of the beams. And as output, we get production drawings, assembly drawings. The very last two slides are about a project, very strange. We decided to test this technology on a real project before proposing to some clients to use this material for facades. This is my garage, and I decided to make a test on my skin, we say in Italia. I decided to test it on myself if it works. And I wanted, there was a challenge in the office. I said, we needed to assemble all the elements in less than 2 days. But us, as me and my colleagues, I said in 3 people, we need to complete the assembly in less than 2 days. So everything must be perfect, everything must be machined off-site, so that on-site we just need to assemble the elements together and learn how it works on-site. And this is the result and the very short movie we created. This is how we nested the elements, how we changed the shape of the elements in order to reduce the waste of material. Then we used a two-axis CNC machine to machine the element. Of course, we increased the speed of this movie. And here you do not need technologies like in the next 50 years. We've been using something which is already on the market. Very simple software, very simple CNC machine. This is the second day, and we completed in the afternoon the assembly. It can be nice, it can be not nice, but what I want to show you is that it doesn't matter the complexity of the material. Timber is it doesn't matter the complexity of the geometry. With timber, we can do this in a very, very, very simple way. So that's it. I hope you enjoyed.